Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to learn about memory management in operating systems, with our focus being on memory management systems. This is part 2 of a series of 9 videos on this topic, which are all posted in MLSwap ICT YouTube channel. My name is Meme JM, or you can simply call me MLSwap. In this presentation, we are going to look at introduction, the strategies or approaches for dealing with memory overload, the classes of memory management systems, which include monoprogramming without swapping or paging, and multiprogramming with fixed partitions. Many different memory management schemes are used. These schemes reflect various approaches, and the effectiveness of any given algorithm depends on the situation. In selecting a memory management scheme for a specific system, we must take into account many factors, especially the hardware design of the system. Each algorithm requires its own hardware support. Several methods have been devised that increase the effectiveness of memory management. All the programs are loaded in the main memory for execution. Sometimes, complete program is loaded into the memory, but sometimes a certain part or routine of the program is loaded into the main memory only when it is called by the program. This mechanism is called dynamic loading. This enhances the performance. Also, at times, one program is dependent on some other program. In such a case, rather than loading all the dependent programs, the CPU links the dependent programs to the main executing program when it's required. This mechanism is known as dynamic linking. The two approaches or strategies for dealing with memory overload are, number one, swapping, and number two is virtual memory. Swapping is a simple strategy which consists of bringing each process in its entirety, running it for a while, then putting it back to the disk. Idle processes are mostly stored on disk so that they do not take up any memory when they are not running, although some of them wake up periodically to do their work, then go to sleep again. Virtual memory allows programs to run even when they are only partially in main memory. Memory management systems can be divided into two classes, which are monoprogramming without swapping or paging, or what we call single process system, and multiprogramming with fixed partitions, those that move processes back and forth between main memory and disk during execution through swapping and paging. So, the two memory management systems classifications are monoprogramming system without swapping or paging, which we also call single process system, and multiprogramming with fixed partitions, which we also refer to as partitioned allocation. Let's look at monoprogramming system without swapping or paging, or what we call the single process system. This management system is also called single partition allocation or single contiguous allocation. It is the simplest possible memory management scheme in which only one program is to be run at a time, sharing the memory between the program and the operating system. All the computer's memory, usually with the exception of a small portion reserved for the operating system, is available to the single application. In this scheme, the system is said to have no memory abstraction. Every program simply sees the physical memory. The model of memory presented to the programmer is simply physical memory, a set of addresses from 0 to some maximum, each address corresponding to a cell containing some number of bits, commonly 8 bits. Under these conditions, it is not possible to have two running programs in memory at the same time. Even with the model of memory being just the physical memory, several options or variations are possible. These options are as shown in the following diagrams, where first, the operating system may be at either the bottom of memory in random access memory, as shown in figure A, or it may be in ROM, that is read-only memory, at the top of memory, as shown in figure B, or the device drivers may be at the top of memory in a ROM and the rest of the system in RAM down below, as shown in figure C. So, my dear students and the rest of the learners, this is simply what I have explained. Under this first allocation, we can see that the operating system in RAM is located on the lowest partition, while user programs are above the first partition or above operating systems. In this other case, case B, the operating system, especially in ROM, is located on the upper portion, or the user programs are located on the lower portion. In diagram C, we can see that we have 3 partitions, with the lowest partition having operating system in RAM. Then the second partition or portion consists of user program, and then we have device drivers in ROM. When the system is organized in this manner, only one process at a time can be running. As soon as the user types a command, the operating system copies the requested program from disk to memory and executes it. Just as a reminder, we talked about a process management, and we said in that topic that when it comes to process management, what is brought into main memory for processing is not the original program, but it is a copy of that program that is converted into a process for execution. Therefore, when this process has been brought into the memory and has been executed, once execution finishes, the operating system displays a prompt character and waits for a new command. When it receives the command, it loads a new program into memory, thus overwriting the first one. Its key advantages is that It is simple and easy to understand as well as to use. However, its disadvantages include: 1, it leads to poor utilization of processor and memory, and the user's job is limited to the size of the available memory. One way to get some parallelism in a system like this one with no memory abstraction is to program without multiple drains. Since all the drains in a process are supposed to see the same memory image, the fact that they are forced to do or to is not a problem. While this idea works, it is of limited use, since what the people often want is unrelated programs to be running at the same time, something the drains abstraction does not provide. Furthermore, any system that is so primitive as to provide no memory abstraction is unlikely to provide a drains abstraction. In contiguous memory allocation, each process is contained in a single contiguous block of memory. So, in this scheme, the memory is usually divided into two portions, one for the resident operating system and one for the user processes. We can place the operating system, just as I have said, in either low memory or high memory. The major factor affecting this decision is the location of the interrupt vector. Since the interrupt vector is often low memory or is often in low memory, programmers usually place the operating system in low memory as well. In this type of allocation, relocation register scheme is used to protect user processes from each other and from changing operating systems code and data. We can place the operating system in either low memory or high memory, just as I have said. However, the major factor affecting this decision is the location of the interrupt vector. Since the interrupt vector is often in low memory, programmers usually place the operating system in low memory as well. In this type of allocation, relocation register scheme is used to protect user processes from each other and from changing operating systems code and data. Relocation register contains value of smallest physical address, whereas limit register contains range of logical addresses. Each logical address must be less than the limit register. The relocation register contains the value of the smallest physical address. The limit register contains the range of logical addresses. For example, relocation equals to 100,040 and limit is equals to 74,600. With relocation and limit registers, each logical address must be less than the limit register. The memory management unit maps the logical address dynamically by adding the value in the relocation register. This mapped address is sent to memory, and the relocation register scheme provides an effective way to allow the operating system size to change dynamically. Even with no memory abstraction, it is possible to run multiple programs at the same time. What the operating system has to do is to save the entire contents of memory to a disk file, then bring in and run the next program. As long as there is only one program at a time in memory, there are no conflicts. This concept is called swapping. Therefore, A system using single contiguous allocation may still multitask by swapping the contents of memory to switch among users. Exposing physical memory to processes has several major drawbacks. Some of these include, number one, if user programs can address every byte of memory, they can easily trash the operating system intentionally or by accident, thus bringing the system to a grinding halt unless there is special hardware. This problem exists even if only one user program or application is running. Number two, it is difficult to have multiple programs running at once. That is taking turns if there is only one central processing unit. On personal computers, it is common to have several programs open at once, such as a 1D processor, an email program, and a web browser, with one of them having the current focus, but the others being reactivated at the click of a mouse button. Since this situation is difficult to achieve when there is no abstraction from physical memory, something had to be done. So let's now look at multiprogramming with the fixed partitions, or what we call partitioned allocation. Monoprogramming is common with small computers with simple operating systems. However, it is desirable to have multiple processes running at once. On time-sharing systems, having multiple processes in memory at the same time means that when one process is blocked, waiting for input/output to finish, another one can use the central processing unit. Two problems have to be solved to allow multiple applications to be in memory at the same time without them interfering with each other. That is, protection and relocation. Chunks of memory can be labeled with a protection key and a comparison made between the key of the executing process to that of every word or every memory word that is fetched. However, this approach by itself does not solve the latter problem, although it can be solved by relocating programs as they are loaded, but this is a slow and complicated solution. A better solution is to invent a new abstraction for memory. The address space must, as the process concept creates a kind of abstract CPU to run programs, the address space creates a kind of abstract memory for programs to live in. An address space is the set of addresses that a process can use to address memory. Each process has its own address space, independent of those belonging to other processes, except in some special circumstances where processes want to share their address spaces. Somewhat harder is how to give each program its own address space. However, this was made possible with the use of base and limit registers. Using base and limit registers is an easy way to give each process its own private address space because every memory address generated automatically has the base register contents added to it before being sent to memory. In many implementations, the base and limit registers are protected in such a way that only the operating system can modify them. A disadvantage of relocation using base and limit registers is the need to perform an addition and a comparison on every memory reference. Comparisons can be done fast, but additions are slow due to carry propagation time unless special addition circuits are used. So, if we accept that multiprogramming is a good idea, we next need to decide how to organize the available memory in order to make effective use of the resource. One method is to divide the memory into fixed-sized partitions. These partitions can be of different sizes, but once a partition has taken on a certain size, then it remains at that size. There is no provision for changing its size. There are a few drawbacks or problems to this scheme, such as, number one, as the partition sizes are fixed, any space that is not used by a particular job is lost. Number two, it may not be easy to state how big a partition for a particular job means. Number three, if a job is placed in, say, Q3, it may be prevented from running by other jobs waiting and using that partition. To cater for the last problem, we could have a single input queue where all jobs are held. When a particular partition becomes free, we search the queue looking for the first job that fits into the partition. An alternative search strategy would be to search the entire input queue looking for the largest job that fits into the partition. This has the disadvantage, or this has the advantage, that we do not waste a large partition on a small job, but has the disadvantage that smaller jobs are discriminated against. Smaller jobs are typically interactive jobs, which we normally want to service first. To ensure that small jobs do get run, we could have at least one small partition or ensure that small jobs times. Using fixed partitions is easy to understand and implement, although there are a number of drawbacks which we have already outlined in this presentation. Therefore, one way of achieving multiprogramming is to divide the memory into unequal partitions. Partitioning can be done manually when the system is started up. When a job is started, it is put in the input queue for the smallest partition that is large enough to hold it. Since partitions are fixed, any unused space in the partition is lost. With the bunch systems, organizing memory into fixed partitions is simple and effective. Each job is loaded into a partition when it gets to the head of the queue. It stays in memory until it is finished. With the time-sharing systems, the situation is different. Sometimes, there is not enough main memory to hold all the currently active processes, so excess processes must be kept on disk and brought in to run dynamically. The following diagrams illustrate how this system of fixed partitions and separate input queues looks. Figure A shows fixed partitions with separate input queues for each partition, while figure B shows fixed memory partition. So, my dear students and the rest of the learners, you can see that in figure A, in this figure A, we have different queues for specific processes that fit to go into a particular partition. So every partition has its own queue, but for figure B, all the processes queue on one line or in one queue, and then based on their sizes, they are taken to their respective partitions in which they fit with little or no wastage. The disadvantage with this method of sorting incoming jobs into separate queues becomes apparent when the queue for a large partition is empty, but the queue for a small partition is empty. For example, in figure A, partition 1 and 3, that is in this figure A, partition 1 and 3 apply to such a situation. An alternative is to maintain a single queue as shown in figure B. As shown in figure B, as you can see, this is figure B. And this is the single queue that we are talking about. So whenever a partition becomes free, the job closest to the front of the queue that fits in it could be loaded into the empty partition and ran. Since it is undesirable to waste a large partition on a small job, a different strategy is to search the whole input queue whenever a partition becomes free and pick the largest job that fits in it. Note that this algorithm discriminates against small jobs as being unworthy of having a whole partition, whereas it is desirable to give small jobs the best service and not the worst. A solution is to have at least one small partition allowed. Another approach is to have a rule stating that a job that is eligible to run may not be skipped over more than a certain number of times. Each time it is skipped over, it is given 1 point. When it has gained a certain number of points, it may not be skipped again. With that, we have come to the end of this subtopic. Congratulations for viewing and listening to this video on memory management part 2 under the memory management systems. You can also listen to all the other parts of memory management, that is part 1, part 3, all the way to part 9, as well as other topics in ICT, computers, or ICT and computers field from MLSwap ICT YouTube channel. You can also access more videos on various ICT and computer topics by visiting and subscribing to MLSwap ICT YouTube channel. In addition, for you to be able to access free life skills, motivational and inspirational resources, visit MLSwap Motivation YouTube channel. For any further correspondence, kindly write it to us through the email mlswap@gmail.com. May God bless you and thank you for listening to me.